Well, change the focus when I hit record.
Sorry about that. Let's see if I can turn some of these off. Leave some on. That's better. All right, so remember the things that affect the brems spectrum and what affects the characteristic spectrum. The only thing that affects the characteristic spectrum is whether or not we're going to have that 69 kVp spike. So the only thing that affects the characteristic spectrum is kVp. Did we have a high enough tube potential to get to 69 kVp? Yes or no? That will determine whether or not we've got a characteristic spectrum. So mass has no effect on the characteristic spectrum. The effects on exposure are direct. If you double your exposure, it doesn't really matter if you're using MA or time. The overall mass is what we're talking about. And we'll talk about MA and time individually later in the semester, but for right now, the only thing that we're talking about is mass. So regardless of how we arrive at the mass, if we double our mass by either doubling our exposure time or doubling our MA, it doesn't matter. The effects are the same, and that is that we directly change the patient exposure, image receptor exposure. The brems spectrum just elevates, the bubble goes up. So looks like that. So at one mass level, notice you've got this area under here, which just represents the number of X-rays. At the low energy end, you don't have any change. High energy end, you don't have any change. Characteristic spectrum is represented in exactly the same spot on both of them. The average represented by the peak of the bubble doesn't change. The only thing that changes is the height of the bubble. That's it. Just the number of photons that you create. So what we're going to talk about this semester regarding mass are the effects of changing mass on beam quantity and its result on patient exposure, and because we have an increase in patient exposure, what that does to image receptor exposure, how that can affect image quality, and how to manipulate the components of mass, that being MA and time, to our advantage so that we can either limit exposure time or actually increase exposure time for our benefit on imaging. The effects of image receptor exposure and image display whenever mass values are too high or too low, and certainly patient exposure as well, and the effects of mass on the image and how it should affect the index number. And the index number is your S number, so to speak, and in some of your systems we tend to focus on the S number. And some of your systems, that index number is going to move in different directions at different increments for a given exposure. And what I mean by that is that in some systems, as you increase your image receptor exposure, the index number goes down. So there's an inverse relationship. And some systems, as you increase your image receptor exposure, that index number goes up. And some of it's pretty drastic, like in some systems, maybe normal exposure is 200. In some systems, normal exposure may be 1, not 100, 1, okay? So across the different manufacturers, we've got different index numbers that are representative of image receptor exposure. So we'll talk about the effects of mass on those. So voltage rectification, we talked about voltage rectification both Friday of last week and last semester, and that is taking a single phase or a full incoming line voltage waveform and inverting it so that we would double the output of the machine, right? So it's changing of alternating current to direct current really is the definition of voltage rectification, but in our case what we do is we don't just change it from alternating to direct, because we could do that just by cutting off the inverse voltage, right? Alternating voltage or alternating current goes back and forth and back and forth, and we could make it direct just by removing the part that goes, backwards. But we don't do that. We take that backwards wave and we flip it up so that we get two pulses going in the same direction. Okay, so when we talk about voltage rectification, that's what we're talking about. So it has to happen after the high voltage transformer. All right, so now you got to think about why that has to happen. What was the purpose of putting the rectifiers after the high voltage transformer? That's one reason. There's really two. That's one reason we only want direct current going through the tube, because inverse voltage could break our filament. So absolutely valid. But what else? What kind of current do we have to have the transformers work? We have to have alternating current. So if we rectify and have direct current before any of the transformers won't work. So we have to have alternating current up to that point. So it has to happen after the high voltage transformer. And voltage rectification increases the output, and not in the way that we would think. Again, there's so much stuff that seems like it should be logical that isn't. We go from single phase to three phase. We got a number one, we got a number three. What's the difference between those? It's a factor of three, right? But it doesn't, you would think that going from single phase to three phase, you would have triple the output, but you don't. It's about double the output, right? So how does that affect the brems spectrum? Well, we get an increase in numbers. We get an increase in numbers, but because our voltage waveform, which is really representative of those pulses, never drops to zero, then what we have is a more consistently high tube potential, okay? So since it never drops to zero, what we get is an increase in higher energy X-ray photons. It's not like it eliminates the low energy X-ray photons, it just gives us a higher likelihood of having higher energy photons. So that gives us a higher average. So it takes and it increases the height of the bubble and it pushes it towards the high energy side. But remember, only one thing affects the characteristic spectrum, that is kVp. The only thing that affects the peak energy is kVp. The only thing that affects the minimum energy is filtration. So this affects everything else though. It affects the height of the bubbles, so it gives us a greater output by a factor of 2, and it also gives us a higher average. So with, you've got 3 different really types of generators. One type you're never going to see unless you go to a dentist's office. Hopefully you go to the dentist once in a while. But that is where you've got half wave and full wave. Half wave is where you're only using half of the voltage waveform. So those are typically low output X-ray tubes like what you see in the dentist's office. You don't need a whole lot to penetrate the teeth, right? So they're very low energy X-ray units, and the more modern units, if your dentist is a newer dentist office, they have a handheld X-ray unit. Anybody seen these things? I had to take a picture last time I was in the dentist's office. It looks like a little gun, and they just stick it next to your mouth, and they shoot X-ray with this handheld unit. It's pretty wild. So very low output, and that's what we call a self-rectified unit. The voltage waveform across the X-ray tube is low voltage, and the low voltage limits the likelihood of reverse voltage. All right, so it's single phase, and the X-ray tube becomes the rectifier. So it's low voltage, it becomes direct current at the X-ray tube, and that's the only place you're ever going to see that. It's in a dentist's office. So that's half wave. Full wave, if you ever work in a doctor's office and they do diagnostic X-rays in the doctor's office, you'll see a full wave, and we call it full wave because you use the full wave. Okay, so you double the pulses. But most likely what you're going to be working with, and certainly what you're going to be working with in a hospital, are 3-phase units. Most of the time those will be high frequency. So the voltage waveform on single phase and any kind of single phase, the voltage ripple is going to be 100%. It's just the difference of how long it's going to stay at that zero voltage, level. Three-phase never drops to zero. Your voltage ripple is 14%. 12 pulses down to 4%, and then high frequency is 1% or less. So you get almost a constant potential. You set 100 kVp, and at least with the electrons traveling across the tube, that is consistent in the travel across the tube. It doesn't fluctuate all that much. All right. So we've been through all that. Let's see. So we're going to take a look at this. So we got three different waveforms, single phase. Notice, what does the peak represent? No, this represents kVp, right? The peak of the bubble, I'm sorry. Peak of the bubble represents, I'm sorry, we're all out of phase there. Okay, the area under the bubble represents numbers, but the very height of the bubble represents average. So the position of that point represents average. So, the height of it represents numbers, so we go from single phase, three phase to high frequency. What happens to that height? It increases, so we get an increase in output, but it also pushes the very top of that towards a high energy side, so we get a higher average, right? So minimum is unaffected, maximum is unaffected, position of the brems, or the characteristic spectrum is unaffected. What we get is an increase in numbers and a push towards a high energy side. Okay, so the effects on patient exposure. All right, whenever you're taking your test, make sure that you understand the test question, because the test question may come at you in one of two ways. It might be asking you things like, if you increase your kVp by 15%, reduce your mass, cut it in half. That's your 15% rule, right? What happens to your patient exposure? Goes down. It goes down, right? So you may have a question that asks just that. You increase your kVp and you reduce your mass, and that maintains your image receptor exposure, but your patient exposure goes down, right? So you may have a question about that. What happens to your patient exposure? What happens to your image receptor exposure with your 15% rule? Image receptor exposure remains the same. Patient exposure decreases, right? But you may have questions that just ask about one thing. Don't read too much into those. If you increase your kVp, what happens to your brems spectrum? The bubble goes up, the energy goes up, you get more interactions inside of the patient all the way across the board, so your patient exposure goes up. Okay? So just don't read too much into it. If we're talking about voltage rectification, if you change from a single phase to a three-phase unit, and you don't change anything, then what happens to your image receptor exposure? Single phase, three phase, and you don't change anything. It goes up. Single phase, three phase is going to go up, right? Because the height of the bubble goes up, even though the average goes up. That doesn't really play a whole lot of a part here, but the height of the bubble goes up. You get a greater output when you change from single phase to three phase. So patient exposure goes up, image receptor exposure goes up. Okay? So, don't overthink things and think, well, if the question just asks you what happens to exposure when you change from single phase to three phase, any kind of exposure goes up, right? Don't make that leap and say, well, if an image receptor goes, or if our voltage rectification goes from single phase to three phase, then I should cut my exposure in half, which you should. But the question didn't ask you that, right? So don't overread the question, just answer the question as it's presented. All right? So if no changes to your technique are made, then patient exposure is going to go up. image receptor exposure is going to go up. So what we do to compensate for that is we change our mAs. Most of your compensations, whether they be technical compensations or compensation for pathologies, most of your compensations are going to involve mAs. Okay, so unless you're looking for an increase in penetration, your technical compensations are almost always going to be mAs, unless you need a change in penetration. Okay, so to compensate, we're going to use mAs always. When we go from single phase to three phase, we're going to have to decrease our mAs. As we go from three phase, single phase, we're going to have to increase our mAs. And it's always going to be by a factor of 2. So what we're going to talk about is the effects on patient exposure, image receptor exposure, image quality, and the technical compensation for the generator type, which we just talked about. Now I want to pause here and talk about the difference between image quality and X-ray quality, okay? Because they're not the same. As a matter of fact, there's a little bit of an inverse relationship. We say X-ray quality, X-ray beam quality is primarily affected by what? KVP, right? But what does an increase in KVP do inside of the patient? What do we get more interactions of? Scatter radiation. What's scatter radiation do to the image? Yeah, it makes it foggy. Okay, so also don't make that leap and say, well, as KVP goes up or average goes up, we'll get a better quality X-ray. No, we don't. We get a better quality X-ray beam. The quality of the X-ray image might actually suffer. Okay, so X-ray tubes. We've got 2 different types of X-ray tubes. Again, you're only going to work with one. In my entire career, I've only ever seen one diagnostic X-ray unit that utilized a stationary anode. And that was an old portable. This portable was so old that it didn't have collimators, it didn't have a light, it didn't have a housing. It had to have housing. You couldn't see the X-ray tube itself, but there was nothing there. And you couldn't tell that you made an exposure. It was an old portable unit, and nobody ever used it because really it was by that point illegal to use it. But it had no rotor button, it had nothing. Okay, so you're never going to see these things, but still it's a testable thing. So you got stationary, you got rotating anode. Both the anode is just a support for the target. Stationary anode may be used in low exposure applications, like again in a dentist office, but as far as diagnostic tubes, you're just never going to see them. And rotating anodes allow for a much larger heat load, and they extend tube life because try to beat it into you last semester. What's the main thing that kills your X-ray tube? Heat, right? So anything that we can do to reduce the amount of heat that we either create or that we concentrate in one place increases the tube life. So the rotating anode takes where you bombard that anode, and instead of having just one little bitty area that you deposit all those electrons, hot electrons on, it's going to spin it around and around so that you can spread that heat out over a much larger area. Okay? So the main 2 components inside the X-ray tube that we've really kind of beat to death are the anode and the cathode, right? So the anode is the positive end of the X-ray tube, the cathode being the negative end of the X-ray tube. The source of electrons is the cathode. So the anode consists of the rotor, and that's the entire portion that rotates, including the stem, the bearings, the entire thing. The stator is the electromagnets, and they're actually outside of the X-ray tube. You don't have the electromagnets inside of the tube. They're outside of the tube, but they're inside of the tube housing. Okay? So you'll see some questions that say, what's the only part of the X-ray tube that is outside of the envelope? Well, what's the envelope? The glass or metal, yeah, the thing that maintains a vacuum. So that is what we recognize as the tube itself is the envelope, right? So they're outside of the envelope, but they're inside of the housing. So your questions will say the only part of the the X-ray tube that is outside of the envelope are the electromagnets, or the stators, okay? The target area is just a specific area on the disk. The entire disk itself is not the target. The target's just what we call the focal track. And it just goes around and around the specific portion of the target. So that's your focal track, and that's your actual area of bombardment. Then you've got the cathode end, and the cathode has subcomponents as well. You've got the filament. The filament is the source of thermionic emissions, right? That's what we heat up. We get glowing red hot, and then we apply the voltage, and then the electrons travel across the tube. So we got two in most X-ray tubes. You got a large and a small, and they are independent of each other. And what I mean by that is that if you apply too much heat to your small filament and you burn it out, the large filament's still going to work. So, you know, they're kind of in parallel with each other, or they're not, you know, connected in a series. One is independent of the other. You burn one out, the other one still works. So you might think, well, that just provides a backup. Well, that's not the purpose for the tube. The purpose for the tube, being large and small, is one sustains a higher heat load, and the other is for fine detail, right? And then you've got the focusing cup that surrounds it, and the purpose for the focusing cup is to compress those electrons. Because again, back to last semester, what are electrons? Little negative charges, right? So you take two like charges and you try to push them together, and what do? Right, so we also talked about the number of electrons that we're going to use, right? We measure them in milliamps, but we said an amp was a ridiculous number of electrons. So even if we take 1/1000th of a ridiculous number of electrons, we still got a ridiculous number of electrons, right? So we're going to have a ton of electrons around this thing, and we're going to try to, you know, put them on this filament, and they're going to have a tendency to try to push each other apart. So the focusing cup, the purpose for the focusing cup is to cram them back together so that whenever they travel across the tube, hopefully they'll strike a small area on the focal track rather than a large area. So it directly affects our sharpness of recorded detail. All right? So focusing cup and filament are the components of the cathode end of the X-ray tube. That's what we just talked about. The failure of the focusing cup would be where you don't have a negative charge on it anymore, and then what you've got is blooming of your space charge. Okay, so blooming of the space charge means that those confined electrons are spread out over a larger area, and that's going to reduce your sharpness of recorded detail. So again, the purpose for the focusing cup is to confine them so that you increase sharpness of recorded detail. If your focusing cup doesn't work, they spread out, and you reduce sharpness of recorded detail. So again, filament sources of thermionic emissions. They're made of thoriated tungsten. And again, the tungsten, if you recall, we had the tungsten in both the cathode and the anode, and we had different alloys. But in the filament itself, the purpose for tungsten was that thermionic emissions were good. They didn't burn out very well, very easily. But I mentioned last semester that something Bouchon didn't really cover is that it doesn't warp whenever it gets hot. You know, things get hot, they tend to expand. Things get cold, and they tend to contract. And tungsten doesn't do that. When you heat tungsten up, it doesn't warp. And when it cools back down, it doesn't warp. So, or it doesn't go back to any other condition. So the large focal spots for really high exposures or higher exposures. Small is for detail. Remember, the filament current is controlled by the current through the filament is controlled by the filament circuit. That was a low voltage circuit down at the bottom that we drew last semester, right? So you had the low voltage section of the high voltage circuit, which was before the high voltage generator. You had the high voltage section. The filament circuit was down underneath. All right, so we create the space charge during the prep stage. The higher your MA, the more it heats up. the longer you rotor, the more it heats up, right? So over-rotoring leads to ballooning of the space charge, and again, even when your focus and cup is working properly, if you over-rotor, then what you're gonna have is expansion of that space charge, leading to ballooning. So it increases heat, heat being the main thing that kills the tube, shortens tube life. It leads to a larger actual focal spot. Remember, we've got two different things when we're referring to focal spot, and we'll talk about it later in the semester, and that is the actual focal spot, which is on the anode, the point of impact on the anode, which changes. And then we've got the projected focal spot, and that would be what the patient sees if they were to be looking up into the X-ray tube. So leads to a larger actual focal spot, and that increases our effective focal spot and reduces sharpness of reported detail. So over-rotoring is a bad thing, right? Standing on a rotor and just rotoring up for extended periods of time is a bad thing for all those reasons. But is there a time to stand on a rotor? Is there a time to over-rotor, so to speak? Yeah, there are times. You know, if you're taking a chest X-ray on a baby, that would be one. You know, so there are times. If you're working in surgery and you're having to coordinate your exposure with an anesthesiologist who has turn-off breathing, you got to be on a rotor, you know, because he's coordinating with the surgeon who's injecting. You know, there are times. But as a general rule, you don't want a rotor. You want your rotor time to be as short as possible. All right, so the target is tungsten and rhenium, and the purpose for the alloy here is that the rhenium adds, at least to hit that instead of hard floor, right? The rhenium adds strength. Tungsten is a very, very hard metal, but if you get anything that's very, very hard, it tends to be very, very brittle as well. And we talked about that last semester as well. You know, if you have a tungsten ring, don't drop it on the floor. If it's pure tungsten, it's probably going to shatter. So the rhenium just adds some strength to that. So it's a high melting point. It has good thermal conductivity. Remember, to extend the tube life, we need to do something to deal with that heat, and we dealt with it in 3 different ways. Conductivity, what were those? Convection. Yeah, we had a fan inside to blow it off. Radiation. And then radiation, right. So our target's relatively large, even though our focal point, our actual point of bombardment is very, very small. So the purpose for that big target is to provide, you know, that rotation, but it also gives us an area for that heat to go. So it spreads out across the face of that target and increases the heat load. So the different ways that we can increase the heat load of an X-ray tube is to increase the size of that target, right? So in applications where we're routinely making really large exposures, like CT, cardiac catheterization, those X-ray tubes may have, and special procedures, where our disc may be, you know, what would that be, about 3.5, 4 inches in diameter, theirs may be about 7. So that increases the heat load, okay? So the effects of the target material on emissions are, number one, characteristic spectrum. What is a characteristic spectrum characteristic of? Yeah, it's tungsten, the type of material we use, right? So if we change that material, then we change our characteristic spectrum. All right, so the effects on peak energy, what's the only thing that affects peak energy? KVP. Effects on minimum energy, or the only things that affect minimum energy? Yeah, filtration. So the effects on the average, I don't even know where to go with that. You know, you'll look at the spectrum in the book, the brems spectrum in the book with different different target material, especially lower target material, and you can't really make sense of the brim spectrum in those low energy target materials. So, I don't know. Brim spectrum could be higher, could be lower, depending on the atomic number. Effects on exposure, I don't know, who cares? You're never gonna work with a gold target anyway, right? Characteristic spectrum, we just talked about that. So, and we just really talked about all that. So the effects on the brim spectrum, probably not. The effects on exposure, yeah, so look at these things. So with if we could use a gold target, that'd be great. But the problem with gold is the melting point is significantly lower than what it is with tungsten. Right? So you're probably not going to melt it on your stove top, but it's low enough that our X-ray tubes will just almost be disposable. But you get down here to these low atomic number targets that we use in mammography and brim spectrum, just takes on a totally different appearance than what we're used to seeing. So. All right, so in the X-ray tube, the entire anode rotates. And again, the induction motors being outside of the tube, we're going to call those a portion of the tube, not necessarily a portion of the anode. So it moves the focal spot and it helps to spread out that heat. It rides on the bearings, and we want to protect the bearings. If you remember from last semester, we want the face of the target to be made out of tungsten for all the reasons we talked about before, but the back of the target may be made out of molybdenum, right? And the molybdenum, as well as the shaft, and the molybdenum is it's still a metal. It still has a pretty high melting point, but it's not as good a conductor of heat. We wanted to keep that heat on the face of the anode so that we kept them off of the bearings. Remember, bearings were one of the reasons that a tube might fail is because the bearings get worn out and you can actually hear them, right? We talked about that. You rotor up and you hear, that's an indication that you got bad bearings. So, rides on the bearings, electromagnets in the induction motor turn it. The anode heel effect affects image quality. You've got density differences that we'll talk about later in the semester. And you've also got sharpness or recorded detail differences that we'll also talk about later in the semester as well. So now we've got tube housing. Purposes for the tube housing. Remember, we call it protective housing, and there's really two purposes for it. One is to protect you from the radiation, right, and the patient as well, but also to protect the X-ray tube from you. That's where the oil lives, to cool the tube. There's some shock absorbency in there too, in case you're traveling across the room and all of a sudden your finger slips off of the button and it jerks to a stop. Ever done that? Probably. Well, those jolts can affect the X-ray tube as well. You got a tiny little thin filament, and you shake it enough, and it's gonna break. So it protects the tube, it protects you as well. So collimation, the collimator housing is below the tube housing, the protective housing. You can actually remove, or the biomaintenance can remove the collimator housing. You'll see that happen once in a while. We'll just take the whole thing down. So we have a tendency to think collimation is focusing the X-rays, focusing the light, and it doesn't do that. It just blocks a portion of it. You can't focus X-rays, so we don't want to focus the light. The only thing that you're doing is shuttering, right? So don't think of X-rays or the collimation as mirrors that contract and expand so that you concentrate the light. You don't do that. The only thing that you do is you block a portion of it, right? So you collimate in, all you do is put shutters in front of the x-rays and the light that should be coming out of the tube housing. That's all it does. So the collimator light, two things about the collimator light, and we've talked about one, it's not in the x-ray beam path itself. Because if it was, then you'd have an artifact of a light bulb on every x-ray that you shot, right? So it's off to the side, and it's there for two reasons. One is so that you don't have that artifact, but the other is that x-rays and light diverge at the same rate, okay? So for the light field to be representative of the radiation field, then the spot, the projected field, has to be the same distance to the source in both cases. You follow me? So from the light bulb and from the focus to the patient has to be exactly the same. If you had the light field here, the radiation field here, there would be a difference in divergence, right? So what we have to do is we have to take the light field and we have to put it off to the side so we don't get that artifact. And we have to make this distance to the mirror exactly the same distance as this distance to the mirror, so that at that point, they're parallel to each other. The light field and the radiation field are exactly the same, okay? So the collimator light off to the side bounces through the mirror. The mirror reflects the light field, which should be representative of the radiation field, but it also adds to filtration. Remember, we've got two different types of filtration. We've got inherent filtration. And inherent filtration is, for our purposes, we're going to say whatever you have to have in place to get your filtration up to that 2.5 millimeters of aluminum for it to be legal, right? Can't make an exposure on a patient with a diagnostic tube under 2.5 millimeters of aluminum. Have to have 2.5 millimeters of aluminum equivalent in order to make exposures on patients if your machine operates above 70 kVp. So that's inherent filtration, which means that your glass envelope or your metal envelope is inherent filtration. Your oil, your protective housing, the mirror, and anything that you have to add to get it to 2.5 millimeters of aluminum is all inherent filtration. Is inherent filtration consistent over the life of the x-ray tube? No, because of tanning. Tanning adds to inherent filtration. And then you've got added filtration, which would be anything above that that you add, that's above that 2.5 millimeters of aluminum. It's not that the tanning becomes added filtration, it becomes added inherent filtration. Okay? So the purposes for filtration is to reduce the patient dose. It reduces the patient dose by eliminating those low energy photons that wouldn't do anything except for absorb inside of the patient. So we just talked about all that. So again, the effects of filtration, the effects of filtration on the characteristic spectrum. Well, what controls your characteristics? The only thing that affects your characteristic spectrum is kVp, right? So no effects on peak energy because kVp again. The effects on minimum energy, this is the only thing that affects minimum energy. And because it eliminates those low energy photons, it gives you a higher average. You remember the test score analogy. So the brems spectrum pushes towards the high energy side, and it reduces the height of the bubble, decreases the patient exposure, and decreases the image receptor exposure again, unless you adjust your technique to compensate for it. If you do adjust your technique to compensate for it, what do you adjust? mAs, because unless you're changing penetration, you want to affect the change in penetration, then your adjustment for now is always going to be mAs. If you want to change penetration, then your adjustment is kVp. Right? So that's what it looks like. We got low energy X-rays stop in the filtration, high energy X-rays go through. remnant beam or the useful beam, what you're going to expose the patient to is down here, so you lost numbers, so you reduce the height and you push it towards the high energy side. So notice where it comes off of the zero is in different places, so this is more highly filtered, this is less filtered. Peak energy is unchanged, characteristic spectrum unchanged. Okay. Any questions? That's right, I can't do that because of that open my office too. Any questions? No? All right, we're out of time. We'll pick up there on Wednesday.
How many questions are there?
Not a whole lot, it's 35 questions. And unless, do some editing to it between now and then, 35 questions.
This is the physics test position.
No, it's just.
Oh,